Okay, YouTube, in our last few videos, we've been exploring solving exponential and logarithmic equations. And essentially what I want to do is just kind of work through my examples here in this video, having you try them on your own first and then checking your solutions against mine and kind of also showing you how I might go about solving these in an efficient manner. So taking a look at what we have here, starting with number 9, looks like we have an exponential equation, kind of easy to tell because of this exponent being located, or the unknown being located up in the exponent. So because I have this exponential thing, the very first thing we want to check is, can we rewrite both sides of this equation as having the same bases? And so because I recognize that 16 is a power of 2, one way that we might go about solving this equation here, let's see if it'll let me write on this here, is to rewrite this so that it says, instead of 16 to the x, it says 2 to the power of 4 to the x. So rewriting it this way would be beneficial. And the reason why is because we have 2 to the 4 to the x being this 2 to the 4 times x. This would have to be equal to 2 to the, well, I guess 2 to the first. And that being said, we could say that, well, therefore, we'll put these little 3 dots in a triangle here. This means therefore. 4x is equal to 1. And now we could just go ahead and solve this after having used the one-to-one property to say that x, well, x must be equal to a fourth here. And so using the one-to-one property, we were very easily able to solve number 19 here. One thing that I do want to mention though is, if in a situation like that you had an exponential equation like we do, and you're more comfortable using logarithms, then maybe what we'll do is we'll take the log base 16 of everything on the left hand side and also the log base 16, okay, of everything on the right hand side. It's just that what we end up with here is this log base 16 of 2, which actually does indeed come out to be equal to 1/4. So we get the same thing but in a little bit cleaner fashion. Now number 10 here, I don't know if you've noticed already, this of course is already an exponential thing, but we have 2 bases, and yes, we could also get these on either side of the equation and write them both as being powers of, well, a common base here would be 2. So the left side we could say, well, 2 to the x, it's already a power of 2. On the right side here, we always want to use parentheses. Utilize those as much as possible. We'll say that this is 2 squared to the power of 2x plus 1. So because we have this power to a power property that says we can multiply these now, simplifying both sides, we end up with 2 to the x is equal to 2 to the 2 times 2x is 4x, 2 times 1 is 2. So because this is the truth, I'll utilize this space out over here. Then we could say that the only truth that must follow is that x must equal 4x plus 2, because 2 to the power of this must be equal to 2 to the power of this if and only if their exponents are equal. So let's go ahead and do this. Let's go ahead and, I normally wouldn't do this to result in a negative, but it'll result in fewer steps. We say a negative 3x equals a positive 2 here, but dividing both sides by this negative 3, we get x is equal to negative 2/3. And it's my recommendation that we go ahead and leave this as a non-decimal, but as an exact value here. So looking at these other 2 examples, let's go ahead and take a look at number 11. Number 11 clearly looks like it's exponential as well, but unlike the last 2 examples, I hope you noticed that 3 to the power of x plus 1, we cannot easily write 25 as a power of 3. So because it's not rewritable as the same base as what we have on the left, what we're going to do is we're going to isolate the base here. So get 3 to the power of something by itself, which in this case it certainly is. And then what we're going to do is we're going to take a log of both sides, and of course we would take a log base 3 to undo our exponential expression with a base of 3. So we have log base 3 of 3 to the x plus 1 is log base 3 of 25. So with these 2 canceling out because of their inverse properties, we see that x plus 1 is equal to log base 3 of 25, and we'll divide. We'll subtract 1 from both sides here. Now these aren't like terms, but we want an exact value, so we say log base 3 of 25 minus 1. We're going to go ahead and leave it this way. We say exact value, but also what we'll want to do is get a decimal approximation here a lot of the time. So in this case, we're going to have to use our change of base property. That is to say that we're going to have to rewrite this as the log of 25 over the log of 3, okay, minus 1, to change our base so that it has a base of 10. Or we could have done a base of e, but I'm going to use a base of 10 here. So we'd say change of base formula says we can do this log base 3 of 25 on our calculators, doing the log of 25 divided by the log of 3. And we get a decimal there of about that, and then we say subtracting 1 off of this, we get about 1.92, I guess this would turn into a 10, so about 1.930. So we say x is approximately 1.930-ish would have been our exponent, and certainly a good idea to go back and check this. So to go ahead and go with continuity here, let's go ahead and take a look at our next problem. Now our next problem is our very first of these set that is logarithmic. And so logarithmic equations, of course, what do we know about them? Well, If we know we can get a log on both sides, if we have more than one log, get them on both sides, we could use one-to-one property if they have the same basis. But because we only have one log, then what I know is it's a lot like exponential things where we want to get the log by itself first. So because this log is already on the left side by itself, what we're going to do is undo this using exponential expressions. We're going to exponentiate both sides having the same base. So because our base on the common log is 10, we're going to say 10 to the power of log base 10 of x is equal to 10 to the 1/2 power of the square root of 10, if you want to look at it that way. So because our 10 to the power of a logarithmic thing with a base of 10 cancel out, we get left with x is equal to 10 to the 1/2 power. I also do want to write this as the square root of 10. And while we're at it, let's go ahead and get a decimal approximation for this. We'd say 10 to the 1/2 power of the square root of 10 would be equal to approximately 3.162. So x is approximately 3.162. We're going to look at just a few more examples here, these four, in which we have some logarithmic as well as exponential expressions to look at. So look at number 13 here. Again, it's logarithmic and we have only one log, so our job is to isolate the log. But because we have no coefficient out in front, no constant that's being added on or subtracted off, then what we're going to do is we're just going to go ahead and exponentiate both sides having the same base. So I'm going to cheat a little bit here. We're going to say e to the power of the left side is e to the power of the right side. And these will cancel out, leaving x equaling e to the second power. So this one, exact value-wise, that's really easy to tell you. And then a decimal approximation, well, it's a nice thing that these TIs give us an e to the power of buttons. We say e to the power of 2. We get approximately 7.389. So about 7.389-ish. So now looking at this number 14, another logarithmic equation where we have only one log, and the log is already isolated. So let's go ahead and do this. Let's exponentiate both sides. And because we have a base of 3 on our log, we're going to exponentiate with a base of 3. We say to the 3/2 power here. And here we have just everything that was on the left, log base 3 of x. So again, these cancel out, and we get x equals 3 to the 3/2 power. So that's our exact value. We could also write this as, I suppose, 3 to the 3rd power square root of this. We could also rewrite this as 3 times the square root of 2, okay? Taking out one of our 3's squared. But last but not least, we could go ahead and evaluate this here. Of course, 3 to the power of, in parentheses, 3 divided by 2. We would get about 5.196, so approximately 5.196. So for our last two equations in this video, we're going to look at a couple of exponential expressions here, which clearly one-to-one property is something that I wanted us to use. But looking at the one on the left here, clearly we have 5 to the power of something equal to 5 to the power of something. What you should have done is said, well, then we could use our one-to-one property of equality and go ahead and say that our exponents must have been the same thing to begin with. So subtracting 2x from both sides here, we would get 4 on the left and only 3 x's on the right with our 8 constants. So clearing the right side to isolate our x, let's see, we get 12 on the left, 3x on the right, and dividing both sides now by 3, we end up with a value for x here of 4. So this 4 would be good to go plug back in and check. See, you get the same thing. And now on the last part of this, I like this example because it is clearly a one-to-one situation. I hope it's clear because we have two exponential expressions on either side of the equation. But the thing I want you to notice here is that they're not both written having the same basis. So we say, well, what's a common root, I guess is what we would say, or a common base for 4 and 8. And if you're savvy here, you'd say, well, 4 and 8, I know this, they're both powers of 2. Then what we're going to do is we're going to rewrite them as 2 to a power, and what we're hoping to obtain here, 2 squared and 2 cubed, is an expression where each side has a base of 2. So using our properties of exponents here, our power to a power property, we're going to have to distribute this through to our exponents up here, or at least our two exponent factors. We say 2 to the 4x minus 2 in this case is equal to 2 to the 3x plus 6. So the groovy thing here is that because we have 2 to the power of something equals 2 to the power of something, then it must follow that 4x minus 2 is equal to 3x plus 6 in the first place. So again, using our common algebraic techniques, we're going to go ahead and isolate x. We get x minus 2 equals 6 if and only if x is equal to 8. And again, really easy to go plug back in and check. Cheers.